Welcome. This is the lecture for Chapter 15, A Dynamic Model of Economic Fluctuations. There we go. This chapter is probably one of the most challenging, if not the most challenging, in our textbook, but it's also one of the most worthwhile. I want to emphasize in this chapter the connections between the elements of this model and what you've already learned. The notation can be a little scary maybe, but remember the concepts behind it are things you've already mastered. The IS curve, the Phillips curve, the Fisher equation. So hopefully as I step you through it, it'll be a little more user-friendly. We are going to combine various elements from previous chapters to construct a dynamic model of the economy. Dynamic meaning one that models how the economy changes over time. This is a simplified version of what we call a DSGE model. DSGE, Dynamic Stochastic General Equilibrium. Let's unpack that a bit. GE, General Equilibrium. This means it's a model of the entire economy, not just of one market. It's a dynamic general equilibrium model, meaning it's a model of the whole economy, but that's dynamic. It shows how it changes over time. And stochastic. It's a dynamic model of the economy changing over time, but it includes random shocks. Stochastic means random shocks to the economy, and showing how the economy changes over time in response to those shocks. How it's going to be different from what we've seen before. Instead of fixing the money supply, the central bank, the Fed, will implement a monetary policy rule. Before we modeled the money supply as just, well, the central bank decided to increase the money supply or woke up one morning and decided to contract it. Here they'll have a defined rule for their policy. Next, the vertical axis of the dynamic aggregate demand, dynamic aggregate supply curve will be the inflation rate, not the price level. And we incorporate time so that one period in time will have an effect on the next period. This is the notation we'll use. The subscript T means time period. So Y sub T is real GDP in period T, T minus 1, same thing in the last time period, T plus 1, real GDP in the next time period. If you want to think of these time periods as years, that's perfectly fine. So if I'm recording this in 2020, Y sub T would be real GDP in this year, 2020. This would be real GDP last year in 2019, and this would be real GDP next year, 2021. Now, the model has 5 equations with 5 endogenous variables. They are equations for output, the real interest rate, the nominal interest rate, inflation, and expected inflation. Now, what we're about to do is called structural equation modeling. What that means is we model each part of the economy separately, with each of their own equation. It's called structural equation modeling because you think of the structure of the economy and you model each part of that structure separately. Then after you model each part of the economy separately, you can combine those equations into one master equation. That lets you cancel out a bunch of things, hopefully, simplify terms, to end up with one equation that models the economy as a whole. All right, endogenous variables. Y sub t, output today. Pi will stand for inflation. Pi sub t, the inflation rate today. R, the real interest rate. I, the nominal interest rate. And E pi. E, expected. So here, E sub t, pi sub t plus 1. This is what people expect today about what inflation will be tomorrow. Now, in addition to these variables, we also care about the unemployment rate, which does not explicitly appear in this model. But we know there's a very strong negative relationship between output and unemployment over the course of the business cycle. So implicitly, unemployment is part of the model. If the model shows output falling below its natural rate, we can infer that the unemployment rate is rising above the natural rate of unemployment. These are the exogenous variables, the ones that are just a given, that the model itself does not predict. What, pardon me, Y bar is the natural level of output. What the natural level means is the level averaged over the business cycle, assuming no exogenous shocks. Pi star, this is the central bank's desired inflation rate, their target inflation rate. This is lowercase epsilon. It'll stand for demand shocks. And this, it looks like a V. It is lowercase Greek letter nu. And that will represent supply shocks. There's one, calling it a predetermined variable is fine, I suppose. The model has to start in some time period. No matter when it starts, as an input to the model, it has to include what inflation was last time period. So this is sort of an initial variable that you have to put in. All right, parameters. Alpha, responsiveness of demand to the real interest rate. This is Greek rho, the natural rate of interest. Natural rate of interest. The rate of interest, the real rate of interest absent any shocks. This is phi, responsiveness of inflation to output. Theta sub pi, responsiveness of the nominal interest rate to inflation in the monetary policy rule. And theta sub y, responsiveness of the nominal interest rate to output in the monetary policy rule. These will be much more clear as we get into the model and you can see where they occur. I want to say something about parameters. Sometimes it can get a little confusing what is a parameter and what is an exogenous variable. Very loosely speaking, an exogenous variable is something that is just given to the model from the outside, but it's something that we might want to change. A parameter, very loosely speaking, is a structural feature of the model that is very unlikely to change. All right, and here we go. Equation 1, the demand for goods and services. The demand for goods and services is negatively related to the interest rate, the real interest rate, just as with the IS curve. A higher interest rate reduces investment and therefore reduces output. So output today is the natural level today minus this term. This is the real interest rate today. This is the natural interest rate. This is the what the real interest rate is when the demand for goods and services equals the natural level of output. You can ignore alpha just for the moment. So this is the difference between the real rate and the natural rate. This is exogenous shock. The alpha term represents how sensitive output is to this difference, to the deviation of the interest rate from its natural rate. So it's a sensitivity parameter. Again, demand shocks, they'll be zero on average over time. Equation 2. What determines the real interest rate? This is just the Fisher equation, modified slightly. Usually the Fisher equation is written I, the nominal interest rate, equals the real rate plus expected inflation. This is just written with the real interest rate on the left. So it says the real interest rate today is equal to the nominal interest rate today minus previous expected inflation. Minus expected inflation today. So this is the nominal rate. From it, you subtract the expected inflation rate, what people today believe the inflation rate will be tomorrow. That gives you today's real rate. Equation 3, what determines current inflation? This is essentially from the Phillips curve. Current inflation is affected by three things. First, the rate of inflation people expected in the previous time period. This is what people yesterday believed inflation would be today. This matters because in the previous time period, if people expected, for example, very high inflation today, they're going to write that into contracts. So that will have an effect on what inflation actually is today. It's a bit of a self-fulfilling prophecy. And this term, the output gap. This is the difference between current output and the natural level of output. When output is above its natural level, firms are experiencing rising marginal costs, so they raise prices faster. Think of it in terms of labor. If the economy is producing much more than its natural level, you would expect the labor market to be unusually tight, and thus wages might rise more than typical, which would contribute to current inflation. Supply shocks. A supply shock, a good example is the 1973 Arab oil embargo, when suddenly the supply of petroleum, which was a fundamental input to production of pretty much everything, suddenly shifted left. And this phi is the sensitivity parameter. How much inflation responds to the output gap. Equation 4. This is an easy one. Expected inflation. What determines what expected inflation will be? Adaptive expectations means that in a very simplified model, and it's not terribly unreasonable, that the best guess people can have about what inflation will be tomorrow is it'll be the same as today. So today, people expect inflation tomorrow to be whatever it is today. Basically, they're expecting the current pattern to continue, and they're extrapolating it into the future. Now, equation 5, the nominal, what determines the nominal interest rate? It is a monetary policy rule. The preceding 4 equations are all conceptually similar to things you've seen in previous chapters. This one's not. This one's new. And it's a little bit bigger, and you might think it's a little bit scary, but once we get through it, I promise you'll decide that it's just a new friend you're making. Okay. First, the nominal interest rate explicitly becomes the central bank's policy variable. It's what they want to achieve, not the money supply anymore. The money supply is just a means to the end of achieving the nominal interest rate. The money supply is still present behind the scenes. It's just that the central bank will use the money supply not as an end, but as a means to get here. So in this model, the Fed sets the nominal interest rate equal to the nominal interest rate today, sub T, equal to the inflation rate today, plus the natural rate of interest, plus the difference between the current inflation rate and the central bank's target inflation rate. So this is a measure of how far inflation is away from what the Fed wants it to be. This is the output gap, how far current output is from the long run natural rate of output. Here, theta sub pi and theta sub y. This is how far inflation is from where the Fed wants it to be. This, theta sub pi, is essentially how much the Fed, or the central bank generically, cares about that difference. If the current inflation rate is very far from the Fed's target, let's say above, so that this is a positive term, you multiply that by theta sub pi to get how much that difference gets put into the Fed's decision of the nominal interest rate. And the same is true here. Theta sub y is how much this output gap factors into the interest rate. You can think of this as how much the central bank adjusts the interest rate when inflation deviates from its target, and how much the central bank changes the interest rate when output is different from its natural rate. An example of this in a simplified form is the Taylor rule, you may have heard of. John Taylor proposed as a policy matter a similar rule, only he did not use rho and other Greek letters. He actually put in numbers. He proposed that the nominal federal funds rate should be set as a normative proposition to the inflation rate plus 2 plus 0.5 times the difference between the inflation rate and 2%, plus 0.5 times the GDP gap. So 2, 0.5, 2, and 0.5. That would be 2, 0.5, 0.5, and here would be 2 as well. These parameters in the model actually historically modeled Fed behavior very, very well. It, looking backwards, predicted what the Fed would do during the Volcker and Greenspan years quite closely. Paul Volcker was appointed Fed chair in '78. Alan Greenspan after him. They followed this rule. This was created after the fact, but they did what later this simple equation would have predicted. And they kept inflation under control for a solid quarter century, more like 30 years. If you apply this to Fed action before the Volcker administration, the Volcker Fed administration, it did not predict what the Fed did in those earlier years, which is possibly why inflation was out of control in those years before Paul Volcker. This is the actual Fed funds rate in red and what the Taylor rule predicted from '87 to 2013. You can see it's very accurate. It doesn't mean that the Fed was following the Taylor rule, merely that the Taylor rule modeled what the Fed did quite well. The one big exception, notice here, this is the start of the Great Recession. The Taylor rule predicts or recommends an interest rate, a Fed funds rate that would be substantially negative. Well, the Fed really can't do that. This is called a zero lower bound. They can't make the interest rate negative. So that's why there is this divergence. Okay. In the long run, there are no shocks. So both shock terms are zero. And in the long run, inflation will be stable at some level. So these are the conditions for the economy's long-run equilibrium around which it will oscillate over the business cycle. In the long-run equilibrium, output equals its natural rate, which also implicitly says that unemployment will be at its natural rate. The real rate of interest will equal the natural rate of interest. That's more of a definitional term. The inflation rate will be equal to the central bank's inflation target. And inflation expectations will be at the central bank's inflation target. Essentially, it means that people's expectations will be accurate. And the nominal interest rate will equal the natural rate plus the now constant central bank inflation target. Now that we have all of those, we can use these 5 equations to construct the dynamic aggregate demand and dynamic aggregate supply curves. Dynamic because now they can model the economy over time. This, deriving the dynamic aggregate supply curve, is almost trivial. To model the economy, we need both dynamic equivalents of aggregate demand and supply. This is just the Phillips curve. with lagged inflation substituted in for expected inflation. So that's dynamic aggregate supply. Deriving the dynamic aggregate demand curve is not trivial, but I'll step you through it and it won't be so bad. There's quite a bit of math coming up, but I want you to be aware that none of it is complicated math. It's really simple algebra, if that. Mostly it's just adding and subtracting and substituting in things. It's just there are a lot of steps of it, but we'll go through it slowly. Output today equals the natural rate of unemployment, the natural rate of output minus the difference between the real interest rate and the natural rate, and some demand shock. Well, using the Fisher equation for the real interest rate, we can substitute the nominal rate minus expected inflation, because the real rate equals the nominal rate minus expected inflation. So all we've done is substitute a bit of the Fisher equation in for this term. Makes it a little longer, but it's still the same thing. Here, this is the result from the previous slide. Now, with adaptive expectations, people's best guess of what inflation will be tomorrow is inflation today. So we substitute in inflation today for people's expectations about inflation tomorrow. The nominal interest rate. For that, well, we already have an equation describing how the central bank decides what the nominal interest rate should be, which of course they can't determine perfectly. They don't have perfect control over these things, but their target, and they over time will achieve it. This is the monetary policy rule that we saw a couple of slides ago. This is the equation that determines what the nominal interest rate will be. So we'll just substitute that in. Makes it much longer, but by substituting that in, yes, it's uglier, but it lets us cancel out some terms, which gives us this, which is also this. Now, if we combine terms and solve for y, we get this. This much simpler equation is the dynamic aggregate demand curve. Now, I've substituted in A for this bit and B for this bit. In the book, they don't do that. Where I show A here, they have that. And where I show B here, they have that. So if you're looking for A and B in the book, you're not going to see it. The reason why I've done this, I've done for two reasons. First, if I had this in there and this in there, it would be too wide to fit on one slide. But also as a teaching matter, I think expressing it this way makes it easier to see the relationship between output and inflation and output and demand shocks. I think it makes it a little less intimidating and easier to work with. Okay, so here is just a plot of the dynamic aggregate demand curve expressed through this. Notice, just as in ISLM, we have output on the x-axis, but here, instead of the interest rate, we have the inflation rate. This shows that when the inflation rate is above the Fed target, They will change policy that will cause the economy to contract. Essentially, they'll see that the economy is overheating and they'll want to slow it down a bit. Now that we have the equations for, I need to tidy this up. We have equations for dynamic aggregate demand and dynamic aggregate supply. Putting them all together, if we then plug in parameters, we can make numerical predictions. In effect, we're simulating the economy's response to a shock over time. These are some reasonable values. These come from the Taylor rule, which we know does successfully, or at least has successfully predicted Fed policy. So that's a good model of how the nominal interest rate is created. All right. Plugging these in, we do some math, it can make predictions over time. Those values let us approximate the U.S. economy as a whole, and the Taylor rule for monetary policy, which broadly captures the behavior of the Fed. Graphs of the time paths of the endogenous variables after a shock are known as impulse response functions. Here's the impulse, a one-time momentary deviation from equilibrium, and here's the response. As an example, suppose that there's an aggregate supply shock, nu sub t, and the shock is in period t, and the amount of the shock is here, 1. So there's a shock for one period, and then it returns to 0. This bottom graph shows how the dynamic aggregate supply curve would shift up in period t by exactly the same amount of the shock. The dynamic aggregate demand curve would remain unchanged. Inflation would rise and output would fall in period t. These effects reflect in part the response of the central bank, the Fed in our case, to this through its policy rule that would lead to a higher nominal and real interest rate, which in turn would reduce demand for goods and services, which would push output below its natural level. And over time, it would return to where it was. In the periods following the shock, you'd see expected inflation be higher, since expected inflation depends on the previous period's inflation. So it doesn't, inflation does not return immediately to its initial position. Adjustment occurs slowly over time, with inflation slowly going back down as people's expectations slowly return to where they were. There are quite a few more examples of impulse response diagrams showing the predictions of the model. Pages 457, 461, and 463 in your textbook. Take a look at those and see how the model can be used to predict the economy's response to shocks over time. I know this is a challenging chapter, but I hope this lecture has helped as I stepped you through the equations. You will have questions, send them to me, and I hope you enjoyed this lecture. See you next time.